Hello, this is Ajay, TA for NLD course. I'm sharing this solution of midsem. So the first question in the midsem was for a two-dimensional dynamical system. We have given trace and determinant of Jacobian matrix J. So under what condition we get non-linear centers in a dynamical system? Briefly explain why such centers are not considered to be structurally stable. Give any one example of a system that displays center while writing its equation of motion. So let's consider a two-dimensional nonlinear dynamical system. Let J represent the Jacobian matrix obtained after linearizing the given system at some fixed point x star, y star. So this tau is trace and this delta is my determinant. Now I have to look over the classification diagram for centers. So from the classification diagram, you can see this line represents the center. So for the center, we should have this tau equal to 0 and this delta greater than 0. So the condition for centers is this delta greater than 0 and this tau equal to 0. So this is the first part. So if you have given this condition right, I give 2 marks for this. The second part is why centers are structurally not stable. So the condition obtained for center after linearizing system may not hold true on considering the higher order terms. So we actually linearize the system and we ignore the higher order terms. So if we won't have ignored those terms, then we would have get a different condition. So any perturbation due to the considering the higher order term may lead to stable or unstable spirals. So that's why these centers are not considered to be structurally stable. These are actually Broadline cases, and the Broadline cases are not considered to be structurally stable. So for more, you can look over the section 6.3 of Strogatz under the topic like fixed point and linearization. So if you have given this correct, I have given one marks for this explanation. And this second part is the third part is give an example of a system. So the question should have specified, like you have to give an example of a two-dimensional system, not a linear system, not a one-dimensional system. It should have given a non-linear example of a non-linear system, not a linear system. So many of you have given example of a linear system. So, but I have considered that also. I have given 2 marks for if you have given any correct example. So the correct solution should be an example of a nonlinear system. So I have taken this nonlinear system example. So if you convert this into polar coordinates, so it come out to be r dot equals to arq and theta dot equals to 1. So you can clearly see if a is greater than 0, then we will have an unstable spiral, and for a less than 0 we will have an unstable spiral, and for a greater than 0, a equal to 0, we will have a center. So this example is from Strogatz book, and this is actually the correct example. So next question is find the fixed point and its stability for this system, this x dot equals to 1 minus exponential of minus x square. So for fixed point, we have to equate x dot equal to 0. So from that we get a fixed point which is 0. So x equal to 0 is our fixed point. So if you have given, if you had get this right, I gave 1 marks for this. The second part is the stability of fixed point. So if you draw the phase portrait for the given system, you will see the curve will look like this, an inverted Gaussian curve, and since x dot is positive for every value of x, for any x, so the flow is flowing, this flow is directed towards positive x direction. So the fixed point x equal to 0 is actually a half stable. The stable on this side and unstable on the other side. So if we have given the stability analysis, I gave 2 marks for that and 2 marks for the phase portrait. This phase portrait with the flow and the graph of x dot. So 1 marks for flow and 1 marks for this correct graph. So making a total of 2. So the next question is, consider the system x dot equals to x square minus y and y dot equals to x minus y. So linearize the system and find the Jacobian matrix for the fixed point at 1, 1. Find the eigenvector of Jacobian matrix and use it to sketch the phase portrait. So we have given the system. So f of xy is x square minus y and g of xy is x minus y. So let x star and y star be the fixed point. So since x star y star is a fixed point, so the functional value of at the fixed point should be 0. Now let's consider the small disturbance around the fixed point. Let v denotes the component of a small disturbance from the fixed point. So now u dot, so now finding u dot will be this x dot, because since x star is a constant, so x dot is actually a function. So the x dot is equals to this f of xy. So using Taylor expansion of this function, we will get this, and these are the higher order terms. And similarly we will get for v dot. So if we ignore higher order terms, we will get this in the matrix form. It can be written as this. So this is actually a Jacobian that we have to find. So Jacobian matrix at any point x, y is this. Now from the given function we can find the derivative of x with respect to x and y, partial derivative, and so we will get g of this Jacobian at any point x and y, at any fixed point x and y, to be this. And if we evaluate Jacobian at 1, 1, we will get this matrix. So this part is of 4 marks. So 2 marks for linearizing the system, getting this, and 2 marks for putting and then getting this Jacobian at 1, 1. Now the second part is finding the eigenvalues of that Jacobian matrix. So we have this eigenvalue equation. From this you will get eigenvalues to be 1 plus minus root 5 by 2. Now the eigenvector corresponding to this eigenvalue, if you find, then it will give a relation between its x and y component to be the relation between their x and y component should follow this. So eigenvector can be written as this alpha and this some factor into alpha, where alpha is a real number. So if I take alpha equal to 1, then eigenvector is come out to be this. So you can take any value of alpha. You have considered different values. So this is the eigenvector corresponding to the eigenvalue lambda 1. Similarly, I will get for this eigenvalue, I will get eigenvector showing this relationship between its x and y component. And in general, I can write it as this, and if beta is equals to 1, my x2 is this. So I have the eigenvectors and eigenvalues. So if you got the eigenvector correct, I gave 2 marks. Now the phase portrait. Now you can see for lambda 1 is a positive eigenvalue, so the perturbation will tends to grow, and the manifold spanned by x1 eigenvector is actually unstable, and the second eigenvalue lambda 2 is negative, so the perturbation tends to decay, and the manifold spanned by the second eigenvector x2 is stable. So you can see 1, 1 at 1, 1 the eigenvalues are of opposite sign, so this is actually a saddle point. So if we draw the phase portrait, this is for x1, the eigenvector corresponding the eigenvector x1, which is actually growing, and this x2 is showing decaying. So the phase portrait around 1, 1 should look like this. And if you got this correct, I gave 2 marks for this.